We looked at area under curves and hopefully saw what it meant. Area under velocity curve. If you have a velocity time curve and you have the area underneath it, we had that one that looked like that. The area underneath it between two values represented then the change in distance, right? This area underneath this here, the change in distance from this time to this time. It makes sense, right, that this is going to be the change in distance, because working the other way, if you have a distance time graph, the slope of the thing represents the speed, right? The slope of a distance time graph represents the speed. Working backwards, it's not the slope of a velocity graph. That would be finding the derivative even further, right? It's working backwards, it's the area. That's the connection. We're going to use the area to find and use some values here. We're going to try and connect these two things here. We talked about approximating areas by dividing things up. If you want the area underneath this curve between there and there, let's call this A and call this B here. If you want the area underneath that curve, somehow we're using some shape of rectangle. And actually, we don't need them to be that skinny. We don't need that many. So if you have some rectangles here like this, it's the same. I know. Looks different to me. Okay, whether you're using the left or right or midpoint or whatever, well, my rectangles have gone a bit awry here, but that's close enough. I don't know what you want to say here. Using subintervals, smaller intervals. We're going to do that right now here. Okay. We're going to call the width of this thing delta x, change in x, delta x. And we're going to say that the height somewhere in there, each point within here somewhere, there's a point in each one here, right? We can call this point like C1 can be that, and this point can be called C2 and C3 and C4 and stuff like that, right? All of those things. Okay? Each of those points can be a C value here. You could, yeah, we're going to get there. The height of the rectangle, we're going to do the height somewhere. We don't care if it's the middle or the left or the right or whatever. This is not the midpoint, it's just somewhere in there. This is called C1, C2. It's just some point in there. Yeah, you could say Cn is some point in interval n or whatever, I don't know. It's some point, some x value within there, right? Any x value somewhere. And we're looking at the height of this, right? The height of that particular one is going to be called, I got to write it over here. The height of that is going to be whatever this function is, f of C1, right? The height of the first one is f of C1 or f of C2 or f of C3 or whatever, right? F of Cn is height of curve at that value, right? So if you want the area of this thing, it's the sum of all of those things, right? Where can I write it here without making a mess here? We could fill this in since I put it there. I should have put it somewhere else. But the width of the subintervals is the whole distance here. This entire distance, so b minus a, divided by how many? I'm going to use n as the number of subintervals. I shouldn't use n up there, but I'm going to change that after. But n's the number of subintervals. So each one is that wide, right? If it was 10 of them and the span was 50, each one's 5. The area under the curve is then the area of each of those. The area of the first rectangle is going to be f at C1 times delta x, right? However wide that is. Width of the second rectangle is f at C2 times delta x. Plus, we can put dot, dot, dot here if you want, because it's going to be, it's going to be all the way up to f at Cn, I guess, times delta x. Or in other words, the area is the sum, you remember this notation here? Sigma notation? We're going, n is 1 up to infinity here, right? Not infinity. Sorry, not n. I got to use a different letter here. Let's use k or I or something like that. Yeah. I think in the book they use I. Now that I think about it, but let's use k. No, let's stick with k. We had k there. Use k. Let's just let's. But we want the sum of each of these things, right? You want the sum of the area, the first one, the second one, all the ones in between, right? So k might have been a bad one to choose, especially if we're doing f of c k delta x. Yes, you never know. Never know when you're going to offend somebody in calculus.
I'm going to show my brother the same.
What? Well, I think earlier in the year we had f of u, didn't we, or something like that? Now we've got f of ck. Okay. Okay, but now if we want it to be the actual area of this curve, what is that? I like it. If you want the actual area now, what do you have to do to this? We need the limit of this as what happens?
That's x.
Well, I'm gonna do this as you could do as the number of subintervals here approaches infinity, right? Or you could say as the width of the subintervals as delta x approaches 0. But let's stick to this since we've got n in there. It's easier to think about making more and more intervals. This is the area. Without this, then it matters which one you choose, the left or the right or the midpoint or the trapezoid or whatever. It matters where you pick this point to be, right? Because I just said these points are anywhere in there. If you wanted this blue area to be smaller, you'd pick a point on this side. If you wanted it to be bigger, you'd pick a point on this side. As soon as we do the limit as the number approaches infinity, it doesn't matter where the points are in there. It could be the left, the right. Each one could be random. It doesn't matter, right? This is the area under the curve. Sigma notation? Well, if you want now let's do this, 2 to the k here. If you want k being 1 up to 4, it just means put it, we have 2 to the 1, right? Put in 1 plus 2 to the 2. Just put those numbers in from there to there. I'm just using it here to do the shorthand of the sum written out, right? Because actually that's where this elongated kind of S shape for the integral comes from. It comes from this. What we've been doing sort of looks like this, meaning the sum here. We're going to come back to this after once we look at finding some things here. Okay, what does this have to do with that? This, I didn't give you this notation before. You haven't had little numbers on the end of this before. That's what makes it a definite integral. When we looked for the area, do I have a graph down below here? I'm going to flip back to this other graph here just to use a graph we've already drawn. if you want to look at the area underneath any of these things here, if you want the area underneath here from here to here, all of this area, which I'm not coloring in well, it doesn't matter. Okay, over 10 minutes, wow. Time flies when you're
having fun.
writing